Now for the proof of the claim. So proof of the claim, pi1 of x x0 is isomorphic to pi1 of x x1. So this is the proof. First, let me draw a picture. Let's say in my topological space X, I'm not drawing the space X explicitly for convenience of the drawing. Let's say this is point x1 and this is point x0, like this. Let me draw a line like this and call it a map eta. It takes me from x1 to x0, like this. Then around x0 I can draw a loop. Yes, this point should end up on x0, that is understood, but for the convenience of seeing things clearly, I'll not join these two. But this is indeed a loop. Let's call this loop alpha. Oops, sorry. দূর পুরোটা কাটতে হবে। So now now for the proof of the claim. Proof of the claim, pi of x x0 is isomorphic to pi1 x x1. Proof. I'm not writing the or drawing the topological explicitly for the convenience of the drawing. So let me draw a picture first, and let's say this is my point x1, this is my point x0, and I draw a line like this that takes me from x1 to point x0. Okay, let's make that a bit smaller. That will help us. And let's make it a bit smaller too. Okay. All right. Now let's call this yellow path as some eta inverse 1 that takes me from x1 to point x0, like this. And when I reach x0, I decide to go around a loop denoted by alpha. Note that even though I have not joined the endpoints, this is the loop, but I have kept it open just to make this drawing as clear as possible. And after I make this loop like this, I go around this way, and then finally I return to point x1 using this green path denoted by eta itself. And this is very evident, right? Eta and eta inverse 1, this green and yellow line, they're just taking us from x1 to x0 and x0 to x1. They're in the opposite directions. So just like we discussed a bit earlier, that the inverse path is just on the opposite direction of the path we are choosing. That is, if I choose this green path as eta, the yellow is on the opposite direction of eta, and that's why I denote it as eta inverse 1, right? Okay. So this configuration is needed for this proof. We call x1 as the base point. And what we have done in this configuration is that we have induced a loop at x1 by using the loop at x0. So this is a very important thing to understand, that we essentially induced a loop at x0, loop at x1 by using a loop at x0. So this is like induced loop. Okay, now let's define all these terms that we draw in the figure mathematically. So our etas will be defined by this map. Again, this I is just 0 to 1, and this eta takes data from this i's, the interval, and maps it to x such that eta of 0 is x0 and eta of 1 is x1, because the eta takes us from 0 to 1, right? I mean x0 to x1. Similarly, eta inverse 1 is defined by this. Oops, sorry, it should be x1. Okay. Now this induced loop can be constructed by the following operation. What do we do to make the induced loop? Look at it here. First, we go from x1 to x0, right? And how can we do that? Through this map eta inverse 1. Then what we do, we have a loop like this. So we go from x0 to x0 via the loop. Then we go from x0 to x1 via the map eta. So we can express the induced loop by the following operation: eta inverse 1, alpha, and then eta. So given any element, this is a equivalence class of loops. Again, they belong to what? The fundamental group, right? Pi1. At x comma x0, we have induced an unique element. We have induced a unique element. By unique element, I mean the induced loop itself, okay, that we denote with alpha prime, and they're set as this equivalence class. Alright, such that this alpha prime is just nothing but eta inverse 1 alpha eta. Let's call this map between alpha and alpha prime, that is the map between these two equivalence classes that are members of the fundamental groups at those 2 points, as P of n, P of eta, such that it takes my elements from the fundamental group at base point x0 and maps it to the elements of the fundamental group at point x1, right? So to show that this pi1 which has a base point of x0 and this pi1 which has a base point of x1, to show that these two are isomorphic, we need to show that our map Pn is an isomorphism. So we need to show that this map is isomorphic. So whenever you want to show something that is isomorphic, you need to show two things. The first is that, so I write it as isomorphic implies that they're homomorphic. That means it's a homomorphism. And second, this is a bijective thing or a bijective map. So an isomorphic map is just a bijective homomorphism. So let me show the homomorphism thing first. So homomorphism. If you don't know what homomorphism is, or if you can't recall right now, let's say f is some homomorphism on some AB, then if this is the case and f acts on a product AB, then it will just give you f of A and f of B, where the product is defined on the domain set and the range and the image set. That's how you can think of it. Let's say here the product is just standard multiplication, but here this might be a matrix multiplication. However, the product structure is preserved. That's a homomorphism, or a group homomorphism if you're dealing with groups. So how do we show that? It's very simple. We just start with things like this. We start with p eta acting on two equivalent classes, alpha and beta, and these two equivalent classes are on point x1. That's how point x0. That's how it's defined, right? So if you can recall that if we had two equivalence classes of loops, alpha and beta, their product is just alpha beta. And whenever p acts on this sort of elements, that means if my alpha beta equivalence class belongs to the fundamental group at base point x0, it will transfer this alpha beta to the point to an element of the fundamental group at x1. So you can consider that this alpha beta as a single entity like delta, and then Pn is acting on it, and this is just nothing but eta inverse delta eta inverse. So with that in mind, you write it as eta inverse alpha beta eta. Now it's just a matter of mathematical manipulation. We invoke the identity like this, eta and eta inverse 1, and we have thing like this. Now you can write this product again as eta inverse 1 alpha eta, eta inverse 1 beta eta, and this is what? This is nothing but p of eta acting on alpha, and this is nothing but p of eta acting on beta. So p of eta is a homomorphism. Proved. We're done with the half thing. Now we have to show that this p of eta is also bijective. So this is the bijective part. So let's assume that there exists some inverse of p eta such that it is denoted by p eta inverse 1. And what it does is that p eta inverse 1 takes any element of the fundamental group at base point x1 and maps it to pi1. x comma x 0. At first we're assuming it, and now we'll show that yeah, this type of thing actually exists. How can we do that? Again, draw a picture. This time I'm not using different colors. So let's say this is x0. Now you start from x0, and from x0 you go to point x1 via eta, and with eta inverse 1 you go from x1 to x0. So the arrow is like this. And now what you do is that you go from x0 to x1 via eta, you loop around x1. Let's say this loop is alpha prime, and then you come back to x1 and you go back to x0 with using eta inverse 1. So we have the elements of the fundamental groups at base point x1 as alpha prime, right? So our claim is that this P inverse 1 should take alpha prime and send it back to some element of the fundamental group with the base point x0. And just like we did before, we can easily see that this is possible by considering, so this P inverse 1, this P inverse 1 eta is actually possible to define via the operation of eta alpha eta inverse 1. Actually, they're equivalence class of operations. So we write P eta inverse 1 acting on some element alpha prime that has a base point x1 as eta alpha eta inverse 1. Okay, so the inverse actually exists. So this is bijective, because if you have a bijective weapon you can get the inverse. And now as a final check, we want to see, is this P inverse eta is actually the inverse of P? Because if this is indeed the inverse of the map P eta, then if we have a successive operation like this, P eta inverse P eta, it should, and I let's say start with alpha, it should return alpha as well. This is what we will see right now. So let's say left hand side is equals to P eta inverse P of eta acting on some alpha. So first P of eta will act on alpha, and this will give us P eta inverse 1. P is acting on alpha, right? So what's the element that we will have after this action of this operation? We'll have some alpha prime, right? And then I have an explicit representation for this alpha prime, which is denoted by eta inverse alpha eta. And then my P eta inverse 1 is acting on this eta inverse alpha eta, right? So according to this suggestion, or this map that we introduced over here, what I'll have is eta inverse 1 alpha eta inverse 1 again, sorry, not eta inverse 1, rather eta, because here is eta, and then I'll have eta inverse 1, right? And these are just identities, so ultimately I have alpha. So these two groups are isomorphic to each other. Proved. Now that we proved it, I I want to have a small I want to make a small comment is that this homotopic equivalence of path and loops is easily generalized for arbitrary maps as well. If you have, so let me write it down, the homotopic equivalence is easily generalized for arbitrary maps as well. If you have two maps, let's say f and g, that takes you from some x to y, and they're continuous maps, these are continuous, then there exists, if there exists some f, which is another map, that is a map from x Cartesian product with I that takes you to y in such a manner that f of x comma 0 is equals to f of x comma 1 is equals to g of x, then f of x is said to be homotopic to g of x. And again, this map is the homotopy or the homotopy map. Okay.